So another 2 lectures this afternoon. As you'll hear in a minute, Richard's voice is failing a little bit after talking so long to so many of you throughout the week. So I'm sure you'll bear with him. We're trying to set this microphone up so that it picks up his voice a little bit. So please bear with him. And if you're, if you're missing things, ask questions to make sure that they've been clarified. Okay.
Okay. Thank you. Actually, it's just got a lot worse. So, is this doing anything?
Yeah.
Oh, it's hard to read. Okay. So maybe we'll get you to talk some. Let me see this. I'll try to do things without speaking as much as I can. So the main thing I want to do today is like say something about these approaches that go beyond density functional theory. It's clear that it's impossible to do too much, and it'd be bad to try to do too much. But if anything, it's to point some people that actually work on this a little bit of direction, and for people who are not working on it to not be afraid of it. The Green's functions and all that sound really hard in the diagrams, but it ain't so bad. So let's be sure we know what we got. This is rigorous stuff. Definition. Add an electron or remove an electron. And the difference is the gap. You always add relative to something, and it'd be like a Fermi energy. Take an electron from a reference path and add it to the system. Now, that would be this one. You've got one more particle. Or you take it from your system, like a hole, to the Fermi energy. And then you take the difference. And that's just the definition of a gap. There's other things where you promote an electron, same number. And why is that generally less? The energy to promote an electron is lower than the gap defined this way. Somebody.
Nuclear relaxation.
Okay. Another reason though, because that would happen up here as well. Nope. Because that would, when you take that difference, that cancels out between these two. Well, really, this is a plus charge, and that's a minus charge. It's just the absence of an electron and the presence. And when you have them both present, attraction. And you can go through other things to say that, like in a solid, this would be, you could make the two very far apart. And that would correspond to the gap. This difference. If you bring them together, it'll lower the energy. So you'll see this in general in several ways. So let's do, we're going to get to these points, so let's do something I showed you before. Have a field band, photon, gigacon electron, so that's photo emission. And we know that, or at least it makes sense, that the interactions are different for a specific missing electron in this band from just the average, which is what was in density functional theory. And to get, I think I'd really like to emphasize what these things mean that you might see in a book or calculate. So a band would be the energy of an electron, in this case, for a loud negative values at a particular momentum. So on a crystal, you might split from 0, I over A, a beryllium node. You have a band, say 2 bands, and at a particular momentum, you'd have exactly 2 energies. Or in silicon, you'd have exactly 4 energies that are occupied and an infinite number of unoccupied ones. And this is exactly what you get out of some calculation like density functional. You get exact energies. And it's tempting to say that everything that looks like that is independent particle. It's just approximate. But let's keep going. There's some things that are just true. And the independent particle approximation was an approximate version. But the energy that you pull an electron out, the lowest energy, or the lowest energy you put an electron in, is well defined. And that's because if you put an extra electron in, it can't get any lower. It can't decay to anything else. That's it. And of course, this is why your computer works. Those electrons don't have a lifetime. They don't go away. They run around in the circuit and do the things the computer does. And so the electron at that point is just infinitely long-lived if it's a perfect crystal, and all these lower states correspond to filled bands. So I use the word that it's independent particle. If the lower states are filled, period, they're just just can't, this is the lowest state for n plus 1 electrons. And I call this the lowest energy, even though it's not low in that figure, but this represents the distance from here up to the Fermi energy corresponds to the energy that it takes to pull the electron out. And so these are high energy in that sense. It takes more energy to pull out. So this starts leading to the picture of what you call quasi-particles. Right at the edge of the band, they're well defined. And you state you can put an electron in or pull it out. And as you go up in energy, they have the possibility to decay. And so the general picture would be that, let me draw this for metal as well. That's probably even more interesting for metal. Right at the Fermi energy, sometimes I call that mu, and maybe other times these set up. Right at the Fermi energy, the electrons the states are very well defined. Because they can't do anything else. They can't decay to anything. But if you put this state, for example, let's see, so these are empty. These are filled. This state can lower its energy by creating a small excitation, and to conserve momentum, it has to go here. And you can always find ways, because you can excite electrons at the Fermi energy with arbitrarily small energy. So if you go away from the Fermi energy, you can always have a lifetime. But right at the Fermi energy, the states are long-lived, and you can do experiments. If you look up in the solid state textbooks, there's these the Haas-van-Alphen experiments, where electrons go around the Fermi surface. It's really not an independent particle approximation. They're well defined in the true many-body sense. And you can do experiments on them. So keep that in mind. We want to know what should be valid when we do real interacting electrons and what's not valid. Like, it's just not true that this is a delta function, exactly what energy. But it is true that that acts like a particle that's very long-lived or infinite life. And here's an experiment. This is silver, and there happens to be a surface state that gives you a good marker for an energy, right near the Fermi energy, and this is the band relative to that. So this would be a band like that thing that sitting right there just happens to be a state on the surface. A lot of really nice experiments of this type. Now, remember what happened with germanium in the density functional theory when you did these simple approximations like local density? You should try it sometime. You get, depending on exactly what you do, you get a metal or you get a tiny little gap. But in any case, it's just totally not germanium. And if you do an experiment, you find is that those bands that look like these dots. And more, of course, the numbers, like the distance from this point to this point, or the indirect gap of germanium is from the zone center to the zone boundary. Those are known perfectly by other methods. And so the fact is these are very bad. And if you do this improved many-body calculation, you get the solid lines. And it's just remarkable how good it is. And we might talk about how remarkable. And on the left, there's something plotted that's kind of messy. And what it is the bands on the right with the lines just moved over. And the dotted lines are this local density approximation, and the solid lines are the ones from the many-body calculation. And you can see that they just sit right on top of one another for the occupied states. And the unoccupied states are just sort of shifted. So the density function is really giving you a lot of good stuff. It's just that the gap is wrong. You might hear people talk about the scissors operation, which means you take scissors and cut the paper and shift the bands. And it's really pretty good. So that's something that's missing. And the density functional is basically the shifts in those energies. This is too low. I can't really come from there, it seems. Can you hear me okay? Okay, it's working. Like from the neon atom, you just made a mistake in the energies to pull the electrons out. Here at the bottom, excuse me. It's not obvious where the mistake is here because this is just been lined up. This portion of these points to be the same. So you don't know whether the error is in the upper states or the lower states. It's just the difference between them that's wrong. So that's the kind of thing you get with density functional, with the simple density functional. So the many-body methods need to really deal with this in a proper way. Those eigenvalues from the density functional were not supposed to have a clear meaning. And if you go through a many-body technique, you You still make approximations, but you at least have the, right basic approach. And so most of the actual work ignores the lifetimes and just looks at the energy shifts. So, remember the harmonic oscillator? There's a reason for saying it now. We agree that, that if you put in a friction term for a harmonic oscillator and you have a driving force, then the response of the oscillator is given by 1 over, if it's the energy denominator, it's like a resonance is broken. So we know that that this picture corresponds to something like a spring coupled to a mass, resonance frequency maybe 0, and some kind of a friction, like it's sliding on the floor. Or just to be a little better, let's say this thing is coupled with something else that absorbs energy. But the something else could be a whole other set of oscillators that can take up energy, but also they could change the frequency. If you could couple one spring to another, you change the frequency in general. So this would be a system that can absorb energy and it can shift the frequency, which is just what you expect if you couple with something else. So this would be the picture. Same picture I showed in a different way, that if you look at the response, if you set that driving force, to be a delta function, and then you can show that the response can be gotten by the integral of this Green's function. It says force at time t, take t prime causes the response at time t, and so any possible set of responses can be gotten by a whole bunch of delta functions. So this would correspond to a continuum of functions, and this would give the final result for your displacement as a function of time. And the reason that it can be done as a function of frequency is Fourier transform, but this is a function of only the time difference. So there's only one time involved. In fact, it's a time difference. So Fourier transform of that gives you the response as a function of frequency. You've seen this before, I'm sure. Freshman physics, right? Or high school physics. But you probably didn't see it called the Green's function. But that's what it is, because this is the function that allows you to propagate from one time to another time. And here I've written this damping as a function of frequency. And of course that's what usually happens. You may see it in textbooks as just a number or a constant, but in fact, when you couple something, it depends on the response of the something. And in fact, you know it can't be a constant. There are rigorous sum rules that say you can't lose energy all the way out to infinite frequency, because you will just violate causality. It's mine, actually. I always know how to talk. Okay, so let's be clear. A harmonic oscillator, it loses energy, or energy shifts because it couples to something else. So we really just want to give that a different name, and then we'll be close to exactly what we talked about in all of the Green's functions that we need. Schrödinger equation, it's linear in time. And so you don't have the square of a frequency, you have the frequency, which is, frequent energy is h bar omega. And so this would be the characteristic energy which you can absorb, or the energy for a state of the system. And this is now called self-energy. That's supposed to be spelled as energy. That, it's exactly the same idea, but I think you can already see what's going on. The epsilon zero here might be the energy of this band at this point. And you'd say, pull an electron out at exactly that energy. But in fact, this point can lose energy in other ways. Say, the electron can move to this point, then by conserving momentum, you can take a state from below the Fermi energy to above the Fermi energy, and you have the possibility to give the system that much energy. If you didn't have to have only that energy, you could have a whole continuum of possibilities. I see you're kind of looking blank. It's either that it's too easy or too hard. It's too easy in a way, right? But in fact, that's exactly the whole picture. And to actually work it out, it's more trouble, but the expressions for working it out are something that you can really understand. So if I go to the next slide, I think we'll get the point. So there's several kind of excitations. You can move electrons, you can put them in, you can do other things. But here would be a point. Energy is conserved and momentum is conserved. Both. Just must be. But momentum is kind of the easy one to see. Here we pull out the electron and test this momentum. We'll call that K. So, and any excitation can be labeled by a momentum. Momentum is conserved in a system that's periodic. Sorry, if it's homogeneous, it's conserved exactly. And if it's a crystal, it's the Bloch theorem. It's conserved plus or minus a reciprocal lattice vector. But within the room one zone, this is exactly conserved and didn't change a bit when you went to a many-body system. That's just a fact. Energy is conserved. Well, what you're saying, what this is saying is that there's many states with the same momentum. And you can give, in the absorption process or in the response of the system, you can give energies to states at different energies, all with the same momentum. Here we are. I'll put that on again. Same idea. Okay. Now this is the relevant picture. So this is what you'd have if you had non-interacting electrons. I mean, a particular K, and it's just a particular energy. If you now have the real system, the energy of the peak will shift, and you will tend to have a peak. And then I draw something that actually happens in real systems. You may tend to have some energy loss. That it doesn't just broaden the peak, but it has a shape. And this is what happens, and I'll mention some of that later this afternoon. It really happens in real materials, and you get an interpretation. But you tended to give the energy to something at a particular higher energy. And this is what comes up in these strongly correlated systems, which you've probably heard of, like high temperature superconductors. This happens. Nobody understands how they get to be superconductors, but they can see that this sort of thing happens. Okay, so there's some interesting things that happened along the way to using that. And now this is stuff that takes some, there's math behind, but there's something that's really clever. And this is like one of the biggest points that I think one can understand in terms of all this green dysfunction stuff. Proved by Lettinger and Warren in 1960. Was it? You can express the final answer in terms of the final Green's function. Feynman diagrams, if you've had a course, probably you haven't. This is something that you presumably have not had. That you can think of making expansions, though, in ordinary perturbation theory, and you start with the kind of the bare terms. Take the eigenstates of your non-interacting system, and the interactions mix of states. And a Feynman diagram would correspond to something like that. You have a state as energy of someone K, and then it has an interaction and it scatters to another state as epsilon K prime. Right. And this excitation, well, I have 3 lines for this because you have a hole and an electron and an electron. So in fact, you have to draw it differently. This electron continues, but now it's at K prime. You have a Coulomb interaction. Now you have the Feynman diagram arrows, the whole going backwards. We have this energy. And the thing you have to conserve is you have to conserve momentum. K prime minus K. The difference in momentum is equal to K electron minus K whole. I don't want to bore you or claim to be doing everything exactly. The reason Feynman diagrams get so complicated and look ugly, I mean, no, they look pretty, but they look hard to understand, is that you just have to consider all the ways that fermions can work. You can emit a fermion before you absorb it, and that sort of thing. But that's rules that you can learn, and they all look like that. And in particular here, this was one of these states, and it's scattered to other states. And so you'd call that the pair range functions. You're just talking about the way things work in the original system. And so everything you would do in that picture would be in terms of what you would call Green's function for this non-interacting system. And every term would correspond to propagation of an electron from one point to another with the good old single-body Green's function. This object without any self-energy. And that's just perturbation theory. So this very special thing that was done by Lettinger and Warren was to show that you could rearrange all that perturbation theory and make everything a functional of the final result. Right? Sounds backwards, doesn't it? To make the final result the property of the final result. That's really useful. And you've heard this before. Tell me something that we've talked about this week and something that 2/3 of you use in your calculations, where the final result was a function of the final result. What?
Potential.
Potential. Perfect. in the proximate Cohen-Shannon equation. Exactly. And we use the potential is good enough. I mean, that's correct. We usually say density because the potential determines the density. So what you got was the total energy of a density, and it's supposed to be, when you get to self-consistency, it's the final density, right? So a few years before density functional theory, it was a more general theory that the Green's function, and part of the information of the Green's function is just the density. If the whole problem was a function of the Green's function, and so that's a bigger picture than the density functional theory. So why did Hohenberg-Cohen make such a big difference? Well, they figured out that you get as part of the information, the total energy, just in terms of the density. Whereas up here is still in terms of this Green's function. It's still harder to calculate. So this is the bigger theory, broader, but this is the one that's made it way more practical. But they're really close relations. In 1962, Bain gave the conditions that for conserving approximations. Of course, the exact theory was conserving. I mean, it's just exact. It means you conserve momentum, you conserve energy, you conserve number of particles. But an approximation is not necessarily so. And Bain has some really pretty things. I give you reference, but this is like pretty stuff. If you have a divergence of a current is a density minus 1 pi n or something. If you calculate the density one way and the current another, you may not conserve number of particles. And literally, that's a set of conditions that's really quite clear that can be formulated in a couple of lines. That the conditions that you have a conserving approximation, and it really is that there exists some scalar function over the Green's function. I mean, that it exists. That's really the point. Just like there exists an exchange correlation energy as a function of the density, this means there's some functional that exists that is a function of the Green's function. And then you take derivatives, you solve equations by finding variational minima, things like that. And if you always start from something that you take derivatives of, then you'll conserve, then you'll properly, even though it's approximate, of course. And the famous work that really got this particular method called GW going is Deneen in '64. Okay, so I'm actually going to show you I think I left it in some diagrams, but it's just meant to say, oh, these are not that hard. So this thing that's more general, excuse me. The more general function of the Green's function is completely analogous to exchange correlation. And the self-energy is analogous to Cohen-Shannon eigenvectors. There it is. Green's function of time. Okay. That looks exactly like the Cohen-Shannon picture. Epsilon 0 might be well, it's a essentially the potential, and the one bad picture be the potential, what you diagnose a matrix. And it's determined by the potential. This would be like the unit guy plus the average electron potential is the Coulomb, average Coulomb potential. Sigma would be because the cone shell, which is just the potential. And the generalization is this thing that's frequency or energy dependent is the generalization of cone shell. That looks scary. It does. It really does. It's hard to see what all those wiggles mean. So, but don't be afraid. You don't have to actually understand them. Because if you work in the field, you've got to understand them in great detail. Somebody over here was going to work in the field, I think. So you got to understand them. But really, this is all this shorthand. If you look at that term, you start labeling the errors by actual states, you know, like I and J. And you'll find that that's exactly what's in the Hartree-Fock equations. It's just this direct term and exchange term. And the wiggly line is the Coulomb interaction. And there's this exactly what's in that theory. You know, so it's just shorthand for that. And you continue and you see that more or less it's almost exactly true that the GW approximation is Hartree-Fock with a screening function. It's really not more or less, it's essentially, that's what it is. And screening function is a dielectric function, which you know in real sense. You know the general ideas for a dielectric function. You put a charge somewhere and it makes a response. So really, literally, you have this rather simple interpretation. And here it is. The self-energy, I've written it in real space here, but it could be in Fourier space, is an electron comes along and it's coming along and it suffers an interaction with itself, and in essence, and there's a screening that comes from all, the interaction that comes from all the other electrons screening, and that's this Coulomb interaction that's divided, and that should have been epsilon, sorry. So screening, Coulomb interaction, screening by dielectric function, and that gives an effective interaction. And this is the electron continuing. Now I shouldn't have erased this. Erase this thing down over here. It's exactly like coming along. Scattering. The only thing that gets difficult about this, that kind of looks funny, is it's not really an electron interacting with itself. It's that all electrons are equivalent. And so all you know is an electron went in, an electron came out. And there's an interaction. And this is the shorthand for understanding that. And this interaction is really simple. So, when I say here, that's a simple interpretation, and I said this is not quite simple to give in a simple form, but we know the basic idea, and the reason is that we can get the zero of a Green's function easily, but what we want is the final one. So you see a self-consistent thing coming up. Yes, right. And however, what people do is G0, you just replace it by the first step, right? As if it was, you don't do it self-consistently. So this would be the ordinary cone jam range function that we've just written down. The scattering that involves the dielectric function that came from the original cone jam calculation. Excuse me. And it's amazing how well that works. However, I was one of them who said, I don't like this. It's this low order stuff. Why should it be okay? And you made this approximation, you made this assertion that you could just start with cone jam and get something out. And since they moved along a little, and maybe this is a thing to mention to you, most of all. The problem is the starting point. And if the final answer is close to the starting point, then this makes sense. I remember those curves for germanium, where the essentially only difference was the gap. That's basically saying that the wave functions were very good, and it was the eigenvalues that you got out that weren't very good. And if you look at the wave functions that go into this, so density function wave functions can actually be much higher quality, or have more physical content than the eigenvalues of the cone jam theory. Let me see, I'm going to stop here and ask some questions. Because I want to mention that next one in a minute. But how about a question or two?
I was wondering about you mentioned the particle lifetime in the So is it something we can actually measure by experiment in the GW approximation? Because I would have thought that any real excitation in a system that we would actually measure. I mean, GW only gives you the addition and removal of an electron. So can we actually can we measure lifetimes?
Yes, it's the reason. I mean, it's simpler not to do it, but in fact, it's all the theory there, and you can show that, like on that figure that I showed you before. But this would be energy. You have this kind of a peak, which is centered on some epsilon A prime. It's shifted. And many times it looks like this. Just, you just say, oh, that's a broken particle, just like a harmonic oscillator with some head. And other times you get larger interactions and you get this stuff like this. And that just doesn't come from this theory. But, so some things will, and then you can keep going through the approach. And there's some things that just don't work. And that's because this requires higher order effects. Please.
Another question. So basically GW, well, you said it corrects, it essentially corrects the energies, so it gives the right answer if I would add or remove the electron to the system. But that is obviously not the same as having an excitation that conserves particle number. So it's and you said in the beginning that the band gap would be different in the case where I have emission or absorption or where I have an absorption of a photon. like an optical excitation. So I've seen GW being used for calculating optical excitation, but technically it's not correct then, is it?
It's not correct, and you need to go to the next step. And I want to mention it, I just mentioned. I must say, if anybody recognizes it, right here. Has anybody in this group ever heard of that? Yeah, good. It's used in a lot of fields of many physics. And really what it is, it's a two-particle problem. And you just, you know, you can replace everything essentially with two particles. And you wouldn't make exactly this approximation, but you start with two particles and get two particles and some interactions in between. Oh, sorry, two particles means, in this case, it'd be the electron and hole.
So you drew like kind of an analogy between the harmonic oscillator and the Green's function there, linking the force to the displacement in frequency.
Right.
Is that equivalent for the? Is it the Green's function here is for the time-dependent Schrodinger?
So the one that's square in frequency was the harmonic oscillator.
Yeah.
And the linear was Schrodinger, and I hit a lot of things, right? So it wasn't, didn't give you all the details, but basically, this optical absorption is really very much like a harmonic oscillator. It's really like a response to the system, and you didn't change the particle number. You get that in dielectric functions.
And the driving impulse is what?
And then, well, like, it could be many things, but the most common is light. So it'd be the photon field.
So it's like an electric field type thing?
Right.
Okay.
So if it's dipole allowed, then an electric field causes this kind of transition.
And the response is an energy change?
So if you, let's see how we see that. So, photon comes along. This would be, let me just keep going. So electric field up and down, right? And that would cause, depends on whether it's a photon or potential electric field, like whether it's transverse or longitudinal. The photons would be transverse, and if it's transverse, then this would correspond to the electrons having a current, J. That would be up and down, in same frequency. So, correct. Up and down. So if you think about it, it's easy to see for an atom. And the photon field comes along, and there's this motion of the electrons in that atom. And that's all it is for an exciton. So, it really is a dielectric function. You can get the optimal response and the poles, the resonances, and all that out of the theories like we were talking about, including time dependence. Oops, I may be careful. Sometimes, on the right conditions, you get time dependence. It's a functional theory, right? I told you some others where it doesn't work. But the logic is there. So I should. There's a really nice piece of work. And I would like to say it's nice in, you know, in one of these pretty contexts. And you got to know something before you think it's nice. Got to know what's happened in the past. We got those beautiful results for germanium that I showed you. And that's basically because the starting point was so close to the finishing point. If you go to some other materials, like nickel oxide, zinc oxide that some people here worked on, I think, you start with the usual density functional, like local density, and those localized states, like the D states, are just at the wrong place. You have the wider bands and the narrow bands, and just not at the right relative energy. And you then stick that into some other theory, and the other theory has all that wrong stuff too. So if you have a bad starting point, you've got a bad finishing point. And there was just nothing, there was no answer to that question. But there's two things that happened recently, is that people have figured out a lot better things to do than just LDA or some GDA to get closer to the final answer. But this approach was really nice to say, let's make a method, and we will define it by a starting band structure. All energies, of course, real in this case, no lifetime. This is just numbers as a function of k. And find the one that's closest to the final answer, just by least squares minimization. And it's a little bit arbitrary how you define close, but you'd like your peak that comes out somewhat prone to be as close as possible to the state you put in. And the argument is that, well, in that circumstance is when when this low order approximation should be good. And I didn't actually find the right figure. I got it on this computer somewhere to show you, and if I could, I might even be able to find it in the meantime. But this group has made a plot that's better than previous plots of experiment versus theory with this approach. And it covers a lot broader range of types of materials, all the way from germanium to zinc oxide and materials like that, and where it's really just very impressive. And even this work on rares and transition metals and all. So it's gotten to a point where there's some apparently justifiable real results. So, and I think you should pay attention that this hasn't improved the ground state one bit, as far as I know. The density functional is still the right way to get the structures, but you often want other properties. And this is becoming more and more just part of the toolbox of theory to actually relate to experiment. So you should really pay attention that this is useful stuff, and it's going to be useful. And it's not that hard. You know, you're going to work on it. So you've got to work to get everything understood. But everybody else should kind of appreciate the idea, and then there's people in the middle, and that's most of us, including me. So if you want to work on a program, I ask you not to just pull one off the web and come out with an answer. Right? Get the basic ideas at any rate and see what things connect to what. And don't just pull black box and get an answer, because then you will make mistakes. But you don't have to be the expert in the field in order to do that. Okay, so let me go on a little bit more. This is the wrong figure. I looked at figures and I thought there was something else. It was for another method that uses this exact exchange, which is a type of density function. And you can get better answers. On the line means agreement with the experiment. And that correct figure that I talked about looks a lot like this, but for many more materials. And and you're getting it for a better reason than the other approaches. So there exists a better figure that I just don't have with me. So this is with a fixed number of particles. And here I really want to go even less detailed. But we can get some points without any of the theory, without any of the hard theory. So I think we've gotten the point that if you pull an electron out, that's photo emission. That's one problem. If you put one in, that's inverse photo emission. And if they're both there, that's the kind of thing you can measure in optical absorption or scatter in the experiment or something. And if you have an independent electron approach, you just don't get anything that has to do with these electron holes. The fact that there are two particles present. And here's some results. This is absorption on gallium arsenide. And once again, I didn't get the right figure, so I'll have to try to draw something on the board. This is density function, a simple local density approximation that gets this band gap much too small. So if you get absorption, okay, imaginary part of that, excuse me. Get some more. That's how we got. That's what we did. This is what we're looking for. Well, there he says it's a very good guy. So this is saying you get absorption at much too low in energy. And if you do and here's the experiment, the darkest line, and this is one of those theories that tries to correct it. And the real many-body theory does something like this, that it sort of puts the peaks in the right place. And I have another example. This is one that's really good. Calcium fluoride has a very strong excitons. It's the kind of material that is extremely strong optical absorption of a particular energy and very high energies. And here's what you get if you have non-interacting electrons, a cone channel with the usual density functional. It's this kind of peak, and this is pulling it to lower energy. And it's really a big effect. And argon is another example where you just completely change the spectrum. Let me draw something on the forward. What actually happens. Now, it's this light you call it omega. At 0, you have this LDA. And you know the gap's too small. So you do it. This is GEW approximation, and you get everything moved up. And it just requires more energy, and it's because the density function is just making a mistake. So where's the truth for the absorption? Is it here? Is it lower? Is it higher? So GW would correspond to just putting an electron in, taking it out, but not having both there at the same time.
I guess it should be somewhere in between because the gap should be a little bit smaller for the green.
That's the point. This is an approximation, but it's an approximation of something that's true. You know, that there exists energies that you can put electrons in and take them out, and you can mathematically just assume no interaction and take one out and put one in and get an energy difference. But the real problem yes.
You said about TDFT that the successful implementations so far have basically been adiabatic.
Absolutely.
How is that really time dependent? Because isn't that really just moving from steady state to steady state? So aren't you losing the model?
I mean, you're right, it's not time dependent at this deep level. So the exchange correlation function is just not time dependent. But the charge density is time dependent. So let's be sure. So, and I just goofed, but to make this on the board, and I hope you haven't forgotten. So we say that. Remember what GEW meant. It meant this business of band structure and the Fermi energy and putting electrons in or taking them out. Oops, no way. But not both at the same time. One or the other, and that's just what it is. It's supposed to be the propagation of an electron, or a missing electron, a hole, and that's just what it is. It's called a one particle Green's function. And if you want to have both present at the same time, you need to look at this figure. So if I put up here something that's GW, it means this one particle problem, and this is then a big approximation to use that to get the optical absorption, where you don't change the number of particles. But what that curve would mean is you just subtract those two energies. The conduction band minus the valence band for all the kind of energies that are there. And so it's just a mathematical thing that's not justified. But what, and we had the point that we know that the real answer should be lower than the green. So whatever it is, it tends to be lower and put more oscillator strength. It puts the optical absorption lower energy and more of it at low energy. That's two kinds of ways to shift to lower energy. And that's exactly what you see if I'm having just the right diagram. You would see that. And I might be able to get it in some slides that I can leave, that I can send to you a little later. So with those correct slides, you can see that you go from this LDA or GGA type density of states to this GW, to the more correct two-particle calculations, and then you get these exciton effects. Or just a shift of energy in the continuum. And then you made the comment that it's probably between, and I think that's generally right, but just remember, this is just something. It didn't really have a physical meaning, so all you know is that it's there, and then the experience says that the gaps are too low. Let's see what else. There's something else I wanted to say, but I forgot it. Any questions? Because I'm going to stop. So any questions right now? Good.
Fields of GW extraction. How do you decide where to stop? So you've got sort of lots of loops that you could put on. I mean, any line you can add like loops and loops and loops to infinite amounts. How do you decide when it's pointless to add more?
Now, by loops, do you mean self-consistency, or do you mean defining the diagrams?
If you looked at the diagram,
yeah.
You've got sort of any straight line you can add a loop into it
yeah.
to make, you know, and that would be another level of complexity.
The thing that's actually been the experience since the 1950s is that there's certain diagrams you need to sum to infinity, throwing away some others that are the same order. And the most famous one is actually what's used in the W, is this random phase approximation. And it's actually exactly what you already do in the dielectric function. It's but expressed in this diagram language. And this will help understand why those diagrams look like they do. If you think of let's think of a Coulomb interaction, not a photon, just a potential added to the system, then the potential can excite electrons. It's you know, it's a dynamical potential, and so you can excite electrons, and that's what that diagram means. You kick an electron from a occupied state to an unoccupied state, and it comes back together, and that's kind of the lowest order effect. You might say, why does it come back together? Already just the very zeroth order thing about the diagrams, I found confusing at the first. But this thing is called a bubble. It is a screening term, and it just says that the electric field is screened by the electrons, but what we care about is an electric field, and this got modified by the fact that there was the electrons were excited from a lower state to a higher state, but they had to come back together to have an effect on the electric field. Another way to say it is the field causes particles, it causes excitation of particles. And another way to say it is that the way you tell whether the particles are excited or not is you look and you destroy them by checking if they're still there. Okay, maybe that's too confusing. But that had to do with the creation and annihilation operators and how they work if you start going to the quantum mechanics textbooks. But anyway, this is exactly what you get if you had a particle and it has excitations that screen the field. But then this, of course, this is going to happen again. And let me make it smaller. And again. And again. And this one has a very special character that's different from some of the others that you could draw by putting lines across and just all the possible ways. And the special thing is that for an electric field, especially at long wavelengths, you have a potential as a function of Q, which goes like 1 over Q squared. So this is 1 over R in real space. Yes, 1 over momentum squared in reciprocal space. So it's large at long wavelength, or small q. Am I using notation that's familiar? Not everybody says that, huh? So let's think. So we know that Coulomb interaction is 1 over distance. Right? That would agree. And Q is 2 pi over wavelength. So if you Fourier transform the potential and express it in Fourier space, you basically get a long range part that goes like 1 over the Q squared, or like the wavelength squared. And by momentum conservation, if this is Q, that's Q, that's Q, and you've added up this whole set of diagrams that every one of them involves something that would be a Coulomb interaction that's big. And you just have to keep those terms to get a reasonable answer. And keeping that entire series is actually very simple. You do it, and you do it by this. You see that you replace everything later by this screen term. So it's like, sorry if I can say this right. So you can see that if you stop at this point, then everything else looks exactly the same. Right? You erase that, and you couldn't tell the difference because it goes to infinity. And you do 2, and it still goes to infinity. So I think I can represent this better. So if this is I can say this better. If you don't have any interactions, this is what you would call this zero order susceptibility. And the real susceptibility is something that we wrote down earlier. I0 plus Z. I hope I'm going to write this right. Oh. Right. See if it works out. Got to have it there. Sorry. V is the Coulomb interaction. We actually had this equation before, and it's exactly like the difference between a polarizability and a non-linear function. You go back to the textbooks, and it's exactly like that. And this is the polarizability and the 1 over 1 minus the Coulomb interaction times the polarizability. This is this RPA form. Somebody in the audience RPA. Somebody in the audience said, why is it called that? It's a really weird name. But the reason is that here by momentum conservation, if this was Q, that was Q, that was Q, and you just had to keep them to get anything reasonable at long wavelength. On the other hand, you start throwing in these other diagrams. Let's pick one. How about one that looks like this? says is you promote an electron, and then by a Coulomb interaction it scatters to another state. So here, from field state to an empty state. And with this interaction, it's going to a different empty state and a different field state. So it's one excitation and another excitation. But this is Q. This is K. This is Q. This is capital Q. This is K. Capital Q. K minus capital Q. And finally you're back to Q again. Because it's obvious it has to be up to Q. Momentum conservation. But looking down the middle, you get all these different momenta. And they all involve something that you have to integrate over, because all possible capital Q's are involved. And those don't diverge at long wavelength. So that was Bohm and Pine's idea, that all these were sort of cancel each other out because they involve all this possible different momenta. But there's one set that you really need to keep. And then that's the minimum set, and it's the set that's actually used in this GEW approximation. What's the minimum that makes sense? And that's what's used. And it's easy to understand the diagrams without a bunch of, without a mini-mighty course. Now, I know I didn't go through that in enough detail to really follow in detail if you haven't had it before, but you can follow it, and the equations on the previous lecture were what actually gives it to you. Okay. Anything else? Yes?
Can we go to the last slide? This approach can handle many model problems. Under which conditions shall we use GW, and under which conditions shall we use DMFT?
Good. That's really what I want to come to. Yes, good. And I didn't put DFT plus U up there. I want to combine that with the DMFT, but also to make a point of what's the difference. So let's go on. I think that's... Okay, so I wanted to convince you that that's useful, but the DFT really helped us a lot. In a lot of cases, it was a good starting point. In other cases, we had to make some corrections. But it's things like the input to, all antibody calculations have some single body input. I think that's just a fact. If you're doing anything quantitative, you've got to have a starting point. And it's true for dynamical mean field theory, it's true for the GW, and it's also true for quantum Monte Carlo. If you look in the literature, you'll find that the diffusion in the Monte Carlo it's what's called the nodes of the wave function in the mini-body problem, and that has to come from somewhere. And they come from calculations like these. There's other methods that don't require that, but they're much more difficult to do. So anyway, I'm going to change to the other. Let's see. Hold on. I'm going to get it over here so I can see. Whatever he puts it on the screen is so small I can't see it. I gave one of these highlight talks last week, and this is almost the same with some stuff thrown out. But the idea would be to, I'd love for you to ask questions. And I made a title that was meant to say something like, this is different. And so this is my title. And you know what that means? It means that we're going to try to get temperature in the problem and also correlations between electrons. And I just want to be really clear that the density function is super useful. It's a theory of the many-body system that gets some things very well. But we want to go beyond. In these functions, in this method, you can put temperature in the Fermi function, and that gets some properties nicely. But it doesn't get some properties like the goals to say get the transition temperature in a magnet, or some other cases that are strongly correlated. Probably haven't heard of them, but there's some cases called heavy fermions, where usually with rare earth materials, and the mass of the electrons can like be 1,000 times the usual mass. And it's because of these many-body effects that make it hard for the electrons to move. So the place where this occurs is when you have localized states, and that occurs in the transition metal with actinides. So this is the place. The GW approximations really worked well when states were very spread out and kind of delocalized like in a semiconductor. And that's when it's really important to take care of this long wavelength stuff well. So you really need it. But if you have these systems, you tend to have band structures that look like this. As a function of K. Nice wide bands that come from the S states of the atoms. So if you look at the 3D transition metals, there's almost all of them, there's the S states and the D states that are about the same energy. You put them in a solid, and you get there's 5 D bands. So you get 1 S band and 5 D bands, and the Fermi energy is in here somewhere. And it looks like a mess. And because they're narrow bands, that means if you look at them in space, they tend to be made of these D states. These temperature states that are much more localized than the S states. I'll exaggerate them. Not really. In the next atom, so basically the bonding is determined by the other electrons, and the D states tend to be more localized, and that's what the transition metals, and so you can think of them as rather localized states. And in that case, you want to consider interactions that are all those states that are really quite large. You put 1 electron on, it requires much more energy to put a second electron there. And you don't care about the long wavelength properties particularly, because you're only calculating stuff, or you're only caring about what's on 1 atom. And you'd like to do both, but this piece of the problem is worrying about things in very short wavelength. This very, just around 1 atom, and that's where the big interactions are. So you really, then you get a rather different theory, a rather different approach, but it's still different aspects of the same ideas. So you'd really like to do calculations that would tell you something about these localized states. And we know from experience that the usual density functionals like the LDA do a bad job of these localized states. I think somebody in here was working on zinc oxide. So you have all these nice semiconductor bands. I don't even know what the band look like exactly, but and then down here somewhere these states. This is energy plotted vertical. And you just find that these are not, you don't describe their energies very well. And with these many cases like this, you add something else to the problem, and in particular, these called LDA plus U. Adds an extra term, an extra repulsive term on one atom that then, on each atom, that then affects these localized states. And you fix the first approximation, you fix that big problem with the usual density functions. I keep saying usual, maybe that's not the right word. With LDA, GGAs, and then you do some of these hybrid functionals, and they put in a little harchy-fuck, and they're better for this effect. So there's other ways to make the improvements. Okay, so I'm sure that many of you, when you get to interfaces like zeolites or zinc oxide, titanium oxide, you'll get to these cases where with the FT, the simplest thing to do is make a correction like this to the density functional. And sometimes it's kind of ad hoc, but you know you really need to do it to make it reasonable answers. So anyway, here's a picture I hope you'll like. It's a periodic table turned upside down in a way. And it's just the transition metals, and it's identifying which ones are very localized and which ones these D states are pretty spread out. And you really get some evidence of this from experiments in addition to things you can bring it out calculations. If you look at these rares, they're just magnetic. Those states are so localized that they're just like spins. That's almost what they are. You just it takes electron volts, many electron volts, to pull an electron out, and it takes many to put one in. And so, for all practical purposes, all they do is have a moment that flips around. Down here, they're extremely band-like, and you can describe them essentially as well as you can gold and silver and other metals. And these tend to form superconductors, which is just the opposite of magnetism. So you can really see experimentally a big difference between those two. The interesting materials are on the border. I say interesting, that's everything's interesting, excuse me. The materials that are very anomalous in this respect along the border, the catalysts like palladium and platinum, the magnetic systems that are most common. There's a huge transition between plutonium and americium way, they tend to just jump from very localized to very band-like, with big change just right there in the properties of the materials. Cerium, I'll show you something for. It can come in two forms at very different volumes. And copper oxide, if you make a compound with oxygen, it pulls electrons off and it's essentially D9. So copper oxide moves right over into that problem. So like with hydrogen materials. So this line really represents things that have a lot of interesting properties. So 3 examples I'd like to ask you to think about what you do the calculation. This is iron and nickel magnetic moments. And 0 temperature, that's what the density functional calculations would correspond to. And they give pretty good moments with the magnetization. But if you go up in temperature, excuse me, the moment goes down and disappears at a transition point. But the magnetism, the average magnetism went away, but the fact that there are magnetic moments around didn't go away. If you look at the susceptibility, I think I have it. It follows pretty well a Curie bicycle. I mean, a whole bunch of little moments interacting with one another in a mean field, the Weiss field, that gives you a susceptibility that goes as 1 over T minus the transition temperature, and it describes the data pretty well. So above the Curie point, there are still magnetic moments. They're just not all lined up. And think about what you get with an density function calculation. There's this famous metal insulator transition in vanadium oxide. It's antiferromagnetic here, go up in temperature, and you can find a crossover between an insulator that's not ordered and a metal. This looks complicated, but what it really is you can take a given material, and with pressure you can change the relative size of matrix elements inside the material, and you can go from an insulator to a metal easily. And at T equals 0, you go from an antiferromagnetic insulator to a non-antiferromagnetic metal. And that would be many of our calculations at T equals 0. Going up in temperature, you have a possibility of going from a magnetic, an insulator that's not magnetic to a metal that's not magnetic with no change in temperature. And that's just strange for our usual band calculations. And it'd also be nice to get good numbers out of a calculation. But just to get the ideas with the first one. Here's a cerium case where you have a magnetic high volume phase and a non-magnetic low volume phase. And this caused confusion for years and years until it's pretty well decided now that this 1F electron, and it's there in both phases. It didn't go away. But what happened was it's almost isolated from the other electrons in a moment in one case, and it's highly mixed in the other case. And it's a huge effect, up to 15% volume change. And I worked on this problem, so I like it. You can even make alloys and with thorium and other materials, and you can find a first order transition with critical points at both ends. I could find one other case in the literature for that, which was tobacco virus and water. But you gotta have something pretty strange. That, like water steam, you go up in temperature and then there's no difference between water and steam. But that's like a liquid gas transition, and this is kind of a quantum liquid gas transition. Anyway, nice stuff, I think. But what do these have in common? It's temperature and correlation. Correlation because the electrons interact strongly. And this happens on these materials. It happens together because in localized states you have a lot of interactions with electrons. They make a magnetic moment. You know that from Hund's rule, from atoms out in free space. And the moment can just vary. So it's low energy excitations, and temperature can affect that. So it goes together. So I'm going to ask you about doing calculations on these three cases. One of those localized states where in a ferromagnetic state, or an anti-ferromagnetic state, or a non-ordered state. This would be a good moment just to, do you have some questions so we can have a discussion? What do you think about that problem? Comments? No? Do any of you work with transition metals anywhere in your calculations? That's a case of ruthenium. Oops, yeah. Yes, so which transition metals? Pardon? Is there current? Oh yeah, sure, is there zirconium, right? Which tended not to be so localized, right? Anybody else? Somebody. Yep.
Yeah, zinc oxide, so zinc.
Zinc oxide, okay. Somebody was working on ruthenium in a large molecule. Good work. And for sure, a transition in these biological molecules is really important. And transition metals are catalysts, and it's just a whole bunch of things that are important. Okay, so should you think of these as spins or as bands? I think that if you get the difference, you'll really be able to understand why there's some controversies, why people think different ways, but you'll be able to think clearly about it. So let's say the ferromagnet. You can think of it as spins that are all lined up, or more correctly, you can think of it as a distribution of density, and if you have a spin up density and a spin down density, you just have more spin up, and it tends to be highly piled up on the iron atoms or whatever. So a density functional calculation would give you the top line, and somebody's spin model would give you that line, and you can see they basically agree. And they turn out to be really good, these DFT calculations, in general. If you get anti-ferromagnet, and you can also see something very similar, but they don't turn out to be so good in those calculations. It's not that it was just the principle wrong, it's just that the approximation weren't so good. Why might that be? Well, this is where something like this DFT plus U comes in. If you, I don't like the word LVA plus U because it's more general. But anyway, so you're adding an interaction, a repulsive interaction that affects two electrons on any two states within one atom. And in general, it tends to repel, and you can put an up and a down spin on these atoms, and that means that you, you have an extra repulsion. So if you actually have downspin here, and it's in the region where this is, sorry, it stabilizes the case while you have downspins and very few upspins. It works against the case where you have up and down spins in the same place. So it tends to stabilize this structure, and it, that was really not the point. And this is one of the big accomplishments of this method, is that it stabilizes some things in antiferrometic structures that turn out to be metals and were just wrong in the other methods. It also increases the energy gap for some very simple reasons. If it's an energy for repulsive energy for 2 electrons, basically, if you have 1 electron in the state occupied, so you're looking at the energy, but the second electron in this state is might be up here, the distance u. We've added this repulsive term to put a second electron there. So here you would have 2 electrons in that state. And you can see why this leads to magnetic order. You have, it leads you, pushes you to the case where you have 1 electron. You have an integer number of electrons on the site. In this particular case, it's 1. And if you try to put 2 there, you pay the price of this repulsive interaction. And so the system will tend to stabilize either the up state or the down state, one of the 2. And you would tend to get a magnetic system, and you would tend to get ordering out of that. And that's what the U actually accomplishes, and it opens band gaps at the same time. Pushes this state up, and so it cures 2 problems. That was just defects in the standard LDA or GGA calculations. And it's really, really useful. And this probably shouldn't have been on this slide because it's different. So the GW is a lot like density functional, and that you have a continuous density. You don't have spins, and it's turned out. This is the point I tried to make earlier, that you can make pretty good, accurate approximations, pretty good accuracy with these calculations, and you can determine what the U is. So here's another answer to that question. The U is very physical and significant, and the LDA plus U and the DMFT are very sensible for these kind of calculations. But it's an ordered state, and if you have a good method, and GW is doing pretty well, you can find the results as well. It just depends on how accurate it is. I'm going to go to the DMFT in a minute, but oh yes, please.
Sorry, I mean you said briefly before you began that the GW tends to be used in the case where you have big, like wide bands, but the U is important where you have narrow bands.
Correct.
So how can you determine one from the other?
Okay. Here's what I would say, was that the GW is an approximation, but we really didn't know how good, and we were always confused by this starting point problem. And so it's turned out that it's been better than I expected by settling on appropriate starting points for materials like this. And when people some time ago did just on top of LDA, it just got bad answers. And now it's actually come around very well. So the GW handles these problems with the long wavelength problems well, and it seems to do pretty well on these localized states. So what doesn't it do, you might ask? And what doesn't LDA plus U do? And so I want to go to that, to this DMFT, but I'd like to point out what's going to be the kind of the major building block for this dynamical mean field theory is that you need to identify some local orbitals, and you need this parameter called U, which is the interaction on those orbitals, and it's already there in this calculation. So those two things are there, and it's just how you use them that's different. Okay, so that's clearly an approximation. You've got to identify that orbital, and you've got to get this effective interaction. Okay, so what was special about those cases? It was either antiferromagnetic, ferromagnetic, paramagnetic, not ordered. Well, what did you do with this case? Yes?
Yeah, can I ask a question? So we use GW to determine U, and then we can use either LDA plus U or DMFT.
Yep. After, yeah.
After U, how do we make this choice? How should we determine with your DMFT?
Oh, okay.
Yeah.
For that.
Yeah.
This is the point. Right. This really is it. How do you do that problem? This is one of those problems that you can find in the discussion, and I think you don't usually find it in the textbooks because it's too hard to discuss. But you find it, people make this comment, is that, well, density function doesn't work at for this average. For this case, that's not magnetically ordered. And it's because you do the density functional calculation and you don't have any moments. But in fact, you know you have this susceptibility. You know there's several things that stay there. I don't think I put it in the slide, but there's cases like nickel oxide where you have a gap in this nicely ordered antiferromagnetic state, and it still stays there when it's disordered, even though it shouldn't. So it's these Mott insulators are particular cases, and I'll ask you about that in a minute. So what do you do? And so by definition, if you don't have time reversal symmetry broken, that means that at every point in space, the probability of finding upspin is equal to the probability of finding a downspin. So if it doesn't have magnetic order, this is just true. It's correct. But the question is that what you care about? That is what you have in a cone-sham problem, because all you have is a density. Or you have two densities, an up and a down for a magnetic system. And you don't have anything else. And so it's just true that in a cone-sham system, if it's not magnetic, you up and down are equal. And it's not only true, it should be true. So here's that picture again. How do we understand those moments at high temperature in iron? Or how did we understand the way the moments went away as temperature increased? Excuse me. The moments didn't go away, the average magnetization decreased. So really the question you could ask to answer the problem is, what's the mean square fluctuation? So at any moment, if the average density is the same for up and down, at any moment, that's not true. At any point in space, there's an average mean square fluctuation of moments. I'll a bit more on the next slide. So if the density is exactly equal for up and down, the fluctuation is up. There's moments that are fluctuating on the iron, but the average mean square value would be non-zero. And just think about it. This is quantum mechanics. If you look at fluctuations of anything, you'll get a non-zero answer. If you get the fluctuations of charge at a point, there's density correlation. Moments is the same, and the only difference from sodium is that it's big in iron. You get a big effect. But it's just something that's non-zero, and it's something that just doesn't come out of a Conchan calculation. And it shouldn't. And now we know it should be there, right? We know it's big in iron. Can we do a quantitative calculation? And that's why the dynamical mean field theory comes in. So you've simplified the problem to having bands that are these sort of broad bands, some states that are considered to be these localized states, and now we want to treat it either above the Curie temperature or below. We like to do both. And the guiding principle is that it's just like magnets, and which has been known for years and years. Okay. So how many of you had the Curie-Weiss theory in one of your courses? Not many. Many. So what's Curie? So Curie meant that you have magnetic moments and they're fluctuating, and in a gas or something like that, you really do. And in a solid, if the spins are well enough separated, you really do. But if well, that picture shows it, but I want to repeat it here because you'll see it more than once. The idea is, sorry, excuse me, you have moments, but you average over all the moments around, and you consider an interaction between them. So if you have interaction is usually called J. And J spin on one side and spin on another side. Then these spins interact. And if you replace the effect on atom J by the average of all its neighbors, then that would be the Weiss mean field. Just the average of all the neighbors around, and consider that to be working on the central spin. See if this is, it should have done the other way. Let's put J here and I there. So really in the world, you have what's given at the top. If you have a central spin, then there are these neighbors, and the neighbors are fluctuating thermally. And so they act on this central atom, but I didn't write it down on the slide. If the interactions are strong enough, then they can cause a phase transition to an ordered state, either ferromagnetic or antiferromagnetic. And that's because you have coupling between the spins, and you look at the average effect. So if you look at the solid state textbooks, you can get real expressions for this, and probably I should have written it down. But you in terms of these coupling constants and the number of neighbors, you can get the transition temperature and things like that. Okay? But it's a mean field theory. You've done an approximation to approximate the average effect of the neighbors. So the guiding principle of dynamical mean field theory is to do the same thing. You'll treat this state separate appropriately. You'll treat it very well, but you'll replace all the surrounding lattice by an effective field acting on this state. So it can be either ordered or disordered. It's just a state that's in a field, in an average environment, and the average environment may have the whole system may be magnetized, or it may not. And so in either case, you get this mean square fluctuation, but you may have it ordered or disordered. So this would be a picture of a phase transition involving spins. And so you get exactly the kind of behaviors that you see for iron and nickel. If anybody has questions, I'll be very happy. It might help make things clearer. Okay, so what is a dynamical mean field? There's really nice work by these two groups of people. The first ones did this thing that's called infinite dimension. And this was mentioned to me a little while ago to say, what does that mean? It just sounds very theoretical, doesn't it? But really it's been known for a long, long time. And it was known back for essentially all the problems involving alloys, involving spins. If you have one spin, you have its neighbors. I'll try not to make them ordered, they're just what they are. If they're in a line, you have two neighbors. If it's two dimensions, you tend to have 4 or 6 neighbors. And I think you can see that if you go more and more and more neighbors, that they'll average out. So suppose you have 12 neighbors. Then the fluctuations on all 12 will tend, the mean, there'll be smaller fluctuations around the mean. And if you have this d go into infinity, it really means that you have an infinite number of neighbors. And mean field theory is exact because there's no fluctuations around that point. And that's been used in spin systems, it's been used in many systems for a long time. And Metzner and Folhart realized that it can be used in this problem. And so now, theorists like to say it's exact in infinite dimensions. Right? Nice. And it's approximation in finite dimensions. And you can help yourself think about it if you notice something like, how many neighbors does an atom have in base in a cubic? I see somebody counting over there. 12. Okay. Is 12 closer to 1 or infinity? Yes. Depends on how you look at it. There's also a nice tradition in theory that considers things as a function of 1 over number of nearest neighbors. And in that case, it's way closer to infinity than it is to 1. And in this sense of averaging, that's actually the appropriate way to look at it. The average effect goes like the number of neighbors, and the fluctuations go like a higher power of the number of neighbors. So it's a 1 over approximation that's used in quite a few areas of theory. And in that case, 12 doesn't look so bad, or rather, infinity doesn't look so bad. So it's not something you should stay away from. It's kind of a theorist's pet idea. Okay, so what's a mean field? It's also simple. It's simply that if you have a confined electron system, then electrons can hop off or hop back. And that's what the mean field is. Spins, there was a potential interaction or some spin-spin interaction that you were averaging over. But for a quantum system, what you're averaging over is average effect of electrons that can hop with a matrix element that's usually called T. And that's the big effect, is the particles can enter and leave. And it's dynamical because of this picture that if a particle enters at time T, it can leave. Oh, I used T twice, sorry. Okay. Usually you call matrix element T, but I want to use time. Let's call that cap T. I don't know. Anyway, if that's one time, you can leave at another time. And it basically is a dynamical effect, just like excitations in materials, dielectric functions. All these things are dynamical. And you can look at them either in time or in frequency. So that's what's dynamical. And it's really quite simple. It's all you need to know, excuse me, is that you have a system that you want to describe well inside that little circle. And you have it in a bath of the surrounding world that you can exchange electrons with. And here's the picture. Oh gosh, I'm keeping you late. Okay, I'll try to end it real quickly. And anybody has to go, please. Don't feel like you gotta stay. Here's the picture. Take a lattice and keep all the individual electron terms. Don't throw any of them away. So you still have bands, you still have all that behavior. But on the correlation part, when you start putting in interaction, the assumption is that you'll keep correlation inside one little object and one little atom, and you'll do that very well, but you won't treat correlations between these blue atoms. So you'll do this one little atom embedded in something representing all the rest, and that's when you'll do all the correlation, all the interactions. So this is, in principle, you do stuff exact in here, and you have a path around this atom that represents all the rest of the system. So let's do that again. This is DMFT. Two problems going on at once. This has to be done with a many-body calculation, because you have many-body electron-electron interactions inside here. But you want to plug it into a system that has nice dispersion and all. You do the single-body interactions, and putting them together is the whole idea. Keep all in the particle terms, and so the final answer is periodic. You keep all the correlation on this site, so it corrects the periodic, the energies in the periodic system, but it's still periodic. But each one of these is treated the same. It's the same, right? And now you got this nice result. If there's no interactions, it's exact.